Now, so far, I've been encouraging you to think of the two types of line integrals we've seen as being completely different, as being totally unrelated. That is the best way to start, and just make sure that you understand and set these things up. The method of setting up the integral that ends in a dt looks rather different for both of these. So it makes the most sense to treat these as completely different things. But there is a connection. So let's now discuss that. So how are the line integrals of scalar functions, the line integrals of scalar functions, so that's the stuff from last time, and the line integrals of vector fields related. So the setups seem entirely different, right? Because they really are, but we're about to try to connect things as much as possible. So your vector field, f of x comma y, we'll just stick with two-dimensional version, uh, had two components, and over here maybe it was like x squared y or whatever, whatever specifically there it was there. But instead of writing something like x squared y, we're just going to write something super generic, just a function called capital P of x comma y, and we'll have here a function q of x comma y. Okay, so whatever, so if you really had x squared y, and here you had y squared over x squared plus 1, then that's your p, that's your q. But we're not going to, let's not do that here right now. Okay, so let's say you have this, and then you have c is parametrized by the vector function r of t is equal to angle bracket x of t comma y of t, with t going between a and b. So we're trying to stick to a rather generic setup, and let's work out that f of r of t then would be take whatever formula you have here, but you've got to replace x and y. Yeah, so instead of p of x comma y, this would be p of x of t comma y of t. Then here in the next spot, you'd write the q formula, except everywhere there's an x, you'd replace with x of t, and everywhere there's a y, you replace with y of t. So symbolically, a way we could write that would be q of x of t comma y of t. Close angle bracket. Okay, so that's one thing we get because of the composing that we need to do. The other thing we would do if trying to set up a line integral of a vector field is we would need to compute r prime of t. And r prime of t should just be, well, differentiate one component at a time. So we'd have here x prime of t, and we'd have here y prime of t. So if we were to set up the integral of the vector field over the curve, just the way that we normally would, it would end up looking like this. It'd be the integral t values going from a to b, and then it should be this vector dotted with that vector. So let's just write that out. Yeah, so it should be, well, the dot product, so meaning this scalar times that scalar. Okay, so we'll have here p of x of t comma y of t, that scalar times the scalar x prime of t. Okay, then plus q of x of t comma y of t. So that scalar here times the scalar y prime of t. It's just what a dot product is, right? Y prime of t. And then maybe this is technically in parentheses, but we'll have dt then at the end of that. Now the point is we will split this as two separate integrals, yeah, at the sum here. So we have here integral a to b of p of x of t comma y of t, x prime of t, let's write that better, x prime of t dt, that integral, plus integral a to b q of x of t comma y of t, y prime of t dt. Now, it's important to point out that this thingy here, x prime of t times dt, was the thing that was dx. When you set up an integral with respect to the coordinate axes back in when we were talking about line integrals of scalar functions. This part right here, y prime of t dt, that was dy. So actually the problem we have here it's literally, if you just work backwards from the first type of thing, the line integrals of scalar functions, this first integral here, it's actually literally the integral over the original curve c of p dx, while the next integral is the integral over the curve c of the function q, the scalar function q, dy. So that's the connection between these two things. Okay, so and of course another way that this gets written is just integral over c of p dx plus q dy. Now, we have built in all the connections and we've done all the work, but just as a summary of it, let's just write down what happens. So this is all the proof of it, but what really happens in the end is if you have a vector field where is defined, the vector field capital F is defined by two scalar functions p and q. Those are the components, right? The components of a vector field are actually scalar functions or scalar fields. Okay, then the integral over c of the vector field dot dr. Okay, so this as written this is the line integral of vector field. This happens to end up equaling the integral over c of p dx plus q dy. And again, this is just the shorthand notation you see here. It's really this. Okay, but what is this thingy here? This is the line integral, or line integrals, maybe technically plural in a sense, because there's really two of them. It's the line integrals of scalar functions p and q, right? You're integrating p here, you're integrating q there, with respect to the coordinate axes. So with respect to x and with respect to y. That's the connection between these. Again, there is a connection, but in the end, when you're setting up integrals of scalar functions, you should just really use the method we saw last time. And when you're setting up integrals of vector functions, you should use the method that we learned at the beginning this time before we saw the connection. It's just important to point out that there is a connection. That's all.